So far, if you go back to lecture 1 or lecture 2 notes, this is what we had. We have a one-dimensional computational domain. We have, inside the domain, we have prescribed a certain number of nodes. Let's call it n nodes. And these are equally spaced, or at least for now, we are saying let's make them equally spaced so that the derivations are relatively straightforward. Okay. The spacing between the nodes we are calling delta x. All right. And in the last class, after we applied the Taylor series expansions, we came up with this expression. We said that d square phi dx square is approximately equal to phi east plus phi west minus 2 phi naught divided by delta x square. Why approximately? Because we discussed in the last class that there is an error associated with this approximation, and in this case the error is second order accurate. That is, it scales as delta x square. Okay. Another way of writing the equation is to use this I index. So instead of using east west naught, you can write it as I plus 1, I minus 1, and I. Okay. So I is any generic index. So I can scan from 2 to n minus 1, for example, in this picture. Okay. For any I that has a value of 2 through n minus 1, this equation that we have here would be valid. Okay. Any questions there? So I just mentioned that, and those nodes are called interior nodes. Okay. They're not on the boundary, they're interior to the computational domain. 2 to n minus 1. Okay. We cannot apply the same equation for the boundary nodes. Okay, and obviously there are two reasons. First of all, if you want to develop an equation for a boundary node, you must use the boundary conditions somehow. Otherwise, you're trying to solve a PDE without using boundary conditions, and that's not going to work. Okay, so somehow the boundary condition has to come in. That's number one. Number two, if you use the expression that we have here, okay, for the interior nodes, this guy, okay, you run into a problem because you see when you set I equal to 1, you get phi of 0, and there is no 0th node on the left end. Okay. Similarly, when you go to the right end and you plug in n for this first term, you get a phi n plus 1, and there is no n plus 1th node to speak of. Okay. So at the boundaries, because you don't have nodes both on the front and back side for both boundaries, you get into an issue where you cannot use this expression anymore. Okay, so we have to do something special at the boundaries. So before we move on to boundary conditions, let's just say this is our governing equation for 2 to n minus 1, and that represents n minus 2 equations. If you count the number of equations, 2 to n minus 1 is n minus 2 equations. Okay, now we have a total of, you can see here, I going from 1 to n. That's the total number of unknowns we have in the system. Okay, so therefore we should have n equations that we can finally solve. Right now we have n minus 2. Obviously we need to do something about that node and that node, those two. Okay, and that is where boundary conditions come into the picture. So we are going to go over boundary conditions of 3 types. Okay. And this is how mathematicians classify it, and these are the only 3, well, I wouldn't say only 3, but the most common 3 types of boundary conditions that you encounter when you do any kind of physical modeling. Okay, whether it's whether you're doing boundary value problems or initial value problems or solving problems in fluid mechanics or solid mechanics or electromagnetics, these are the typical 3 types of boundary conditions we encounter. Okay, the first one is called a Dirichlet boundary condition, or a fixed or prescribed value boundary condition. What that simply means is that the values of phi at the 2 boundaries are known. They are prescribed. Okay, very straightforward. It's kind of like saying, if I'm solving a heat transfer problem where temperature is my unknown, the 2 temperatures on the left and right ends are known. Okay. So that's what's called Dirichlet boundary conditions. Okay. And we are seeking a solution to our system of equations. So therefore, we can use those directly. So we can say, okay, my phi 1 is phi L, and my phi n, which is my nth node, phi of the nth node, is phi R. Okay? You can think of those two as two equations, basically, right? I mean, they're not coupled to the other equations, but they are equations nevertheless. Okay? So therefore, we have now n equations with n unknowns. As I said, we already had n minus 2 equations. We now added these two equations right here. Okay? And therefore, we have n equations with n unknowns that we can solve. Okay? Now, there's one problem with this approach, and this is a problem that not many people often realize, and this is really what makes finite difference methods not so good as some other methods. Okay? And the problem is that we haven't satisfied the governing equation at the boundary at all. We've just applied the boundary conditions. Okay? Now, if you go back here to what we had earlier, this equation we got from the governing equation for the interior nodes. Now all of a sudden we are saying, okay, we have two boundary nodes, but we don't bother to satisfy that equation, or at least the mother equation, d square phi dx square equal to s phi. We are not bothering to satisfy that at the boundaries at all. Instead, we are saying we are going to use this equation at the boundaries. Okay? Now, is that good? Is that bad? Okay? The answer to that is it is not what is desirable, and there are reasons for that, and I'll explain to you what really goes on. Okay? So, and the reason we have chosen to use the boundary conditions instead of governing equations is because we have to use the boundary conditions. You can't solve a PDE without using boundary conditions, but ideally we would like to satisfy also the governing equation at the boundaries. Okay? So we would like to satisfy both at the boundaries if possible. Unfortunately, we cannot do that in this case. Okay? Now, why do we need to satisfy both boundary conditions and governing equation at the boundaries? All right. Now, think about what happens when we solve a problem analytically. Okay, now we are saying we should satisfy boundary conditions and governing equation at the boundaries. So the issue is, do we really do that when we do an analytical solution? Because an analytical solution is obviously supposed to be exact. Okay, that is sort of our mother of all solutions. Okay, so the question is, do we really do that when we do analytical solutions? So if you think about the steps that we take to solve an analytical, to solve this problem analytically, here's what happens. You start with the differential equation, okay, and you have two boundary conditions. So first thing we do is we integrate this guy twice to get our phi of x, right? So first step is d phi dx becomes s phi times x plus c1, okay? And then second step, we integrate again, it becomes s phi times x squared over 2 plus c1x plus c2, okay? We have two unknown constants. So this equation here is our alternative form of the governing equation. There is no approximation there in going from here to here. It's exact, right? Now what do? To eliminate the two constants, we plug our solution into our boundary conditions. Okay? What does that mean? That means we are not only satisfying the boundary conditions, we are also satisfying the governing equation at the boundaries, because we are taking the solution that came out of the governing equation and plugging it into the boundary condition. Okay? So we are satisfying both when we do analytical solution. So in a sense, it's pretty clear that when we do analytical solutions, we satisfy both. So numerically, when we want to solve the same problem, we should also aim to do both, satisfy governing equation and boundary condition. Okay? So this is something important to remember when you come up with formulations, any kind of formulation, whether it's finite element, finite difference, finite volume, doesn't matter. Your goal should be to satisfy both equations at the boundaries. Otherwise, you are missing something in your solution. Okay? All right. Now, when we have finite difference method and Dirichlet boundary conditions, of course, we want to do this, but we cannot do it because what happens is if we try to do it, we get an overspecified problem or a problem. So suppose I have my two boundary conditions and I also try to use the governing equation. I'm going to get two extra equations, n plus 2 equations, n unknowns. So it's an overspecified problem. Okay, and therefore, does anybody know how you solve an overspecified problem? Suppose you have more equations than unknowns. Anyone? You have to use what are called Lagrange multipliers. Okay, it's an optimization problem. You don't have a unique solution anymore. Okay, you try to find a solution that satisfies all n plus 2 equations in the best possible way. They cannot be satisfied exactly, but you minimize the error. Okay, that's what happens. So it's more like an optimization problem. But that's not what we want to do here. Try to minimize the error. We actually want to solve the exact equations. So we are going to stick with the fact that we just use the boundary conditions, get rid of the governing equation at the boundaries. All right. So if we summarize all the equations we have, our n equations, we have for the first node, we have phi1 equal to phi l. For the interior nodes, we have that equation, that finite difference equation that we derived. In the last equation, we have phi n equal to phi r. Okay, so now we have n equations with n unknowns. And we can solve it. Any questions? All right, so to solve it, for a computer to be able to solve it, we want to set it up as a matrix system, A phi equal to B, let's say. Okay, so that the set of equations can be solved on a digital computer. And therefore, we write it in matrix form. Okay, in a matrix form, this is how it's going to look like. Okay, now one of the things you have to understand is how to go from this equation here to this form here. Okay, I'll try to explain briefly what really goes on. So if you look at the first equation, so each equation is represented by a row in a matrix. That's how you should always fill up the matrix when you program. Okay, sometimes I see people, what they do is they take an element and then they fill up the one on top and then the one on the left. Okay, that is a wrong way of filling in the matrix when you're programming. It just messes up your thinking. Okay, don't do that. Think of each row of a matrix as one equation. Okay, each row represents an equation for a node. All right, so if I look at the first one, this one, all right, what do I have? So now remember, matrix multiplication is row times column. Okay, so what I'm doing is I'm multiplying 1 with phi1, I'm multiplying 0 with phi2, I'm multiplying the third element with this third element, and so on. Okay, so if you look at what we have here, we have basically 1 times phi1 is equal to phi l. That's all. Everything else is a 0. Okay, so if you go back here, that's what we have. 1 times phi1 is equal to phi l. All right. Now, sometimes students ask me, why do you want to include the boundaries in your system of equations? They are knowns. Why don't you just solve for n minus 2 unknowns? Okay, valid question. You can do that. The only problem is, or it's not really a problem, it's really a, what should I say? It's a bookkeeping issue. Okay, so what's going to happen is you're going to set up a system of n minus 2 equations. Your first unknown is really the solution at the second node, right? Your second unknown will be the solution at the third node, and so on, if you solve for n minus 2 unknowns. All right, so what you have to do is you have to be aware of that and then copy the data back into the actual array before you plot it and so forth. Okay, so that's the only caveat there. And when you get to multidimensional problems where you have not 1 dimensions but 2 dimensions and many different boundaries, it becomes a bit of a nightmare thinking about, oh, okay, the unknown that I solved is actually this node. Okay, and copying data back and forth. So a better way to do it is to set up the solution matrix as if the boundary condition, which is really a known in this case, phi1 and phi n, you treat it as an unknown, but you set up the equation in such a way that once you solve it, that boundary condition value is recovered. Okay? Does that make sense? All right, so that's the first row. You look at any of the other rows, basically what you have, for example, for the second row, you're going to have this times phi2 plus this times phi3 plus this times phi4 is equal to S2. Okay. For a generic ith equation, you can see phi I minus 1 times that, phi I times that, phi I plus 1 times that will be equal to Si. Okay. That's how the equation has been written. And then the last equation, again, you get 1 times phi n is equal to phi right. Everything else is a 0. Everybody understand this setting up of the matrix? This is very important, obviously. I mean, it's easy, but this is sort of like the very fundamentals. If you're not able to do this, then things become increasingly difficult down the road. Okay? Any questions? All right. So one thing you notice here is that the system that we got here is a tridiagonal system. It has 3 diagonals. Everything else is a 0. Okay? And the important point to note is that there are not only 3 diagonals, there are 3 diagonals clustered in the middle. Sometimes you can get systems of equations where you have 3 diagonals, but 2 of the diagonals are spaced far away from the central diagonal. Okay? But in this case, we have 3 diagonals which are clustered together. These types of systems are called tridiagonal matrix systems, and they can be inverted very easily compared to full matrices. Okay? And we'll talk about that towards the end of today's class. Any questions so far? All right. So let's move on and talk about other types of boundary conditions. So the second type of boundary condition is what's called a derivative or Neumann boundary condition. So the first one was Dirichlet or prescribed phi. This one, what happens is, now of course I've applied the Neumann boundary condition only at the right end. Left end I've still kept Dirichlet. So don't think of this combination as Neumann or whatever. Okay, this is still Dirichlet. This one here is Neumann. Okay, so the left end I've kept as is. Only the right end I've changed to a Neumann boundary condition. What that means is, instead of prescribing a value of phi, the derivative of phi at the boundary is given. Okay? If you think about a physical problem, suppose again going back to a simple heat conduction problem, temperature is your unknown. Okay? Instead of giving temperature at the right boundary, I'm telling you what the heat flux dt dx is at the boundary. Okay? Any questions? All right. So we talked about that. And so in terms of our nodes, we can say, okay, again, phi1 is phi L. That stays put. Nothing changed there. And at the right boundary, we have d phi dx at n, the nth node, is equal to some constant c. Okay? So now what we have to do is, obviously we can't use that differential form directly into our matrix. Okay, same idea. Just as you couldn't use d square phi dx square equal to s phi, computer doesn't understand that. Same idea here. Computer wouldn't understand that derivative boundary condition. You have to convert it to an algebraic equation before you can use it. Okay. So how is that done? That is done using a backward Taylor series expansion. Okay. Again, remember, our goal, as we said, is to satisfy not only that boundary condition, but also the governing equation at the boundary, both. Okay, a lot of textbooks, what they will do is they will find a finite difference equivalent of that, set it equal to C, and that's your equation, period. That is the partially correct way of doing it, because that again doesn't satisfy your governing equation at the boundary. So don't ever do that. It will give you errors. It will give you poor solution accuracy. Okay, even if you see it in a textbook, don't believe that. All right, that's only partially correct. What we want to do is really satisfy this equation as well as the governing equation at the boundary, if possible. All right, so let's see how we can do that. So we do a backward Taylor series expansion. We've talked about this already. This is in the negative direction, so we get this minus sign here as well as that minus sign there for the odd terms. Okay, so we are expanding phi n minus 1 about phi n. Why are we doing that? Because we want to derive d phi dx at n. That is why n is our pivot point. Okay, and not the other way around. All right, so what we are going to do now is we are going to substitute this d phi dx. Let me clear this out a little bit so we can see these things clearly. So we are going to substitute this guy in here. Okay, get rid of the first derivative using that boundary condition. So we do that. You see d phi dx has been replaced by c, okay, and the rest of the equation stays put. All right, now what do? We rearrange that equation to obtain an expression for d square phi dx square, which is in our governing equation. Okay, so we rearrange to get the second derivative. All right, and this is what we end up getting for our second derivative. You see this higher order term show up, which has a delta x in front of it. Okay, so what we have done here is we have obtained a finite difference approximation of the second derivative of phi, which includes the fact that the boundary condition has been satisfied. Okay, because we plugged in the boundary condition already. That's how we ended up getting this c here. Okay, now it has some error just like for the interior nodes, and it turns out that in this case this expression is only first order accurate because it's delta x to the power 1 as opposed to the interior nodes which had delta x to the power 2. Okay, be that as it may, let's say now we want to satisfy our governing equation in addition. Okay, we have satisfied our boundary condition already. We now want to satisfy our governing equation. What do? We take that expression, plug it into our governing equation, which says d square phi dx square at node n is equal to source term at n. Okay, that's our governing equation. So we've satisfied both boundary condition as well as governing equation. Okay, we can rearrange that into a matrix form, and I'll show you that in a bit. Okay, so in summary, the finite difference equations, we now have our left node stays the same, nothing has changed. Interior nodes, nothing has changed. Okay, right node, we have a new equation instead of phi n equal to phi right. Okay, so again we have n equations with n unknowns. We can set this up as a matrix system and solve for it. Okay, if you do that, here is what it's going to look like. Okay, everything else is the same as before. Let's just look at the last one. Okay, so last one has 2 over delta x squared times phi n minus 1, right? So if you go back here, that's what you have, 2 over delta x squared times phi n minus 1, and then negative 2 over delta x squared times phi n, which is what you have here, negative 2 over delta x squared times phi n. Okay, and on the right hand side we have this guy, Sn minus 2c over delta x. Those are all constants, known values. There are no unknowns there. Remember, our unknowns are the phis. Okay, so that goes into your right hand side right here. Okay, yeah. Oh, the S it would be a known quantity. You know, for example, if you solve a heat conduction problem, this would be your heat source. Okay, inside, so it would have some value. You'll see when, for example, if you look at homework 1, I said, okay, S is equal to exponential of negative x. Okay, so it would be something that's known. Yeah.
So, is being given the derivative more accurate than since you're satisfying both equations of that right boundary?
Okay, so giving the derivative that depends on the problem at hand. You don't have the choice of, you know, if you have a problem where the temperature is known, from that you can't derive the derivative and say that's the boundary condition I'm going to be using. In that case, the derivative becomes part of the solution. Okay. On the other hand, if the derivative is known, then the phi value at the right node becomes part of the solution. So it's not like you have the option of specifying which one you want to. Okay. But I can understand kind of where you're going with this. Yes, the finite difference method would be more accurate with a Neumann boundary condition because of the fact that we can satisfy both with Neumann boundary conditions. Okay, no error is incurred in that case. Yeah.
But that equation is only first order accurate, and the other ones are second order.
Yes, we will get to that in a moment. Just bear with me. Any other questions? Okay, so matrix is still tridiagonal, only the last row has changed. We already talked about this. Okay. Now, this is what he just mentioned. Okay, that the last nodal equation is only first order accurate, and that is not desirable because the lower accuracy of that one node will contaminate the rest of the solution. The rest of the solution is second order accurate. All the other nodal equations are second order accurate. Okay, so ideally, if we want to be really rigorous, we don't want a first order equation for one node and second order equation for all the other nodes. In other words, we don't want to mix and match orders. Okay, so the derivation I showed you, that's first order accurate. You could also derive a second order accurate scheme, and this is how you would do it. You use two backward Taylor series expansions. Remember, we had this rule where we said, you know, to derive something, to increase the order, you have to use more Taylor series expansions. Okay. Okay. So by first order accuracy, we mean, see this error term which we are throwing away. This has a delta x. Okay, instead of a delta x squared. Yep. Okay, so now what we do is we use two backward Taylor series expansions, or two nodes left of n. Okay, so the first one is the one that we already had, okay, which we used to derive the first order scheme. And now we have added another Taylor series expansion of n minus 2 about n with spacing negative 2 delta x. Okay, so everywhere you see 2 delta x squared, 2 delta x cubed, and so on. Okay, and of course we are trying to get rid of, or we are trying to derive a second order, the second derivative. Okay. This guy, we are going to plug in the boundary conditions. So that's equal to c, d phi dn dx at n. Okay, so that we don't have to worry about. So we should aim to somehow get rid of the third derivative. Why? Because the next term will have delta x to the fourth. Okay, and if you think about it, when I divide delta x to the fourth by delta x squared, I'm going to get a delta x squared. Okay, so that's the goal, to get rid of the third derivative, which we were not able to do when we used only one Taylor series expansion. Okay, we just threw away this last term here. Okay, So to get rid of that, obviously you can see I need to multiply the first equation by 8 because there's a factor of 8 here, 2 cubed. Okay, and then subtract the two equations. And when you do that, this is what you get. Now, incidentally, I noticed this morning that there's an error in this last term that I derived. I think in the notes you have 8/6 or something like that. Okay, so just make that correction. It actually comes out to be 1/3. Okay, and you can try doing the math yourself. Basically, what you see is you will get 8 minus, in the fourth term, you will have 8 minus 16, which will give you a 8, divided by 4 factorial. So 8/24 is 1/3. Okay. So that's what we end up getting when we multiply the first equation by 8 and subtracting the second equation. All right. Now we plug in our boundary conditions. So let me just go back. So instead of dphi dx, this is where I use my boundary condition. And boundary condition says dphi dx at n is equal to c. C being a constant. And that's what we have plugged in here. Okay. And now I rearrange that equation to get the second derivative. And this is what I get. This is fairly straightforward. Okay. And you see this term here that I'm left over with has the fourth derivative and delta x square times some constant. Okay. That constant really is not important. Again, you know, there's a mistake in your notes. I think I have it as 1/3 or something like that. But regardless, that number is not important. What's important is that it is second order. Okay. Everybody get that? So leading order error term is second order, which means that we have now a second order accurate finite difference approximation of the last node. Okay. And now you throw away that error term and satisfy your governing equation. So d square phi dx square at n is equal to Sn. So that gives you that. Okay. Any questions? Yeah.
We were trying to make the error term in second order.
Mm-hmm.
So why can't we just take the first order error formulation and then multiply the equation by delta x, and then by substituting the last condition, we can say delta x into d square p by d square equal to Sn into delta x. So we get delta x term in the.
That's not going to give you a second order error. Okay, I mean, your equation ultimately has to be written as d square phi dx square equal to s. So what you're doing now is you're changing the units of the equation. Okay, so the error is the error in the second derivative. The error is not the error in the second derivative times delta x. What you're doing is you're simply multiplying it by delta x. That's not the error in the governing equation. Okay. And what really you're doing is the units of all the other equations now are different from the units of the last equation. Okay, you can't compare them anymore. So you have to have consistent units for all the equations if you were to compare the errors. Does that make sense? Okay, so this is what you end up getting. Again, you know, I've written it in a form that you can finally easily figure out the matrix coefficients. So obviously you can see -7/2 delta x square is going to go into your diagonal. And then 8/2 delta x square is going to go into the next term next to the diagonal. And then there will be another term, -1/2 delta x square, which will be one element farther away to the left of your diagonal. And I'll just show that in a moment. So this is what you end up getting. Okay, so now we have 3 elements show up in the last row. Bad news is that this guy has destroyed the tridiagonal structure of the matrix. Okay, so good news is we have second order accurate period for all the nodes. Bad news is you can no longer use a tridiagonal solver. So again, we come back to the philosophy of no free lunch. You want to get more accurate, you have to put in more computational effort. Okay? And this is one of the reasons why sometimes, and we'll talk about this when we get to more complex meshes and all that, people tend to use first order accurate schemes for boundaries. Okay? But this is the basic procedure and the final outcome. Any questions? All right. Third kind of boundary condition. This is called a Robin boundary condition. Okay, this was developed or formulated by a Russian mathematician named Gustav Robin. Okay. Sometimes in the literature it's referred to as Robin's boundary condition. I don't know why, but those names are used interchangeably. All right. It is also in the physical modeling community known as a mixed boundary condition. So we call prescribed value boundary condition, flux boundary condition, or derivative boundary condition, and then mixed boundary condition. This is nothing but, again, the left one I've retained as is. On the right, what you have is a combination of the sum of the derivative and the value itself equal to something. Okay? So neither the value is specified nor the derivative is specified. It's a combination of the two that's specified. All right? Now, you can see here it's kind of nice because by setting b equal to 0, you can get a derivative boundary condition, and by setting a equal to 0, you can get a prescribed value boundary condition. So in a sense, the mixed boundary condition encompasses the other two. Okay? You can just appropriately set the coefficients to get one of the other two. Okay? So this is sort of, I would say, the most common one. So if you're writing a general purpose program, this is what you program in, and then depending on what boundary condition you want, you can set either a or b equal to 0. Okay? Now, one might say, well, when do you encounter such boundary conditions? Let me just give you an example here. So, for example, in heat transfer, we often say, okay, we have a wall, okay, and let's say this is a slab, okay, so we have conduction heat coming in here, convective heat going out there, so this has H T infinity, convective boundary condition outside. So my boundary condition becomes H times T at, so suppose this is x equal to L, my right boundaries, T at x equal to L minus T infinity, and this is balanced by negative K times dt dx at x equal to L. So boundary condition is negative K dt dx at x equal to L is equal to H times T at x equal to L minus T infinity, where T infinity, K, and H are constants. Okay? So you can see I can rearrange this and write this as dt dx at x equal to L plus H over K times T at x equal to L, okay, is equal to H T infinity over K. All right. So you see, if I compared this to A times dt dx plus B times T equal to C, my A is equal to 1, my B is equal to H over K, and my C is equal to H T infinity over K. Okay. So I'm just showing you this to give you an idea of where these kinds of boundary conditions are used. This is one of the most common boundary conditions, Newton cooling boundary condition in heat transfer. Okay. You encounter these kinds of boundary conditions when you do chemically reacting surfaces and things like that, and lots of different applications. Okay. Any questions? Everybody has it? Okay. So let's just switch. All right. So that was just an example. Okay. And in terms of our nodal values, we can write A d phi dx at n plus B at B times phi at n is equal to C. Okay. Instead of using x equal to L. And we can rearrange that equation and write it like I wrote for the heat transfer equation short while ago. D phi dx at n is equal to C over A minus B over A times phi n. Okay. All right. So how do we do our boundary condition now? Well, we use the exact same procedure as we did for Neumann boundary conditions. We do a backward Taylor series expansion. So that's what we had. Okay. And now this guy I'm going to plug in here for d phi dx. All right. So instead of d phi dx at n, I get C over A plus B over A times phi n. All right. So that guy got plugged in here. And now I rearrange. So this derivation, by the way, I'm showing you is first order accurate only. Okay. Second order, I've already shown you how to do that. You can follow the same procedure, but I'm just showing you how to do a Robin boundary condition with first order accuracy. So you rearrange to get your second derivative, and this is what it looks like. Okay, again, you see here that guy. Okay, first order accurate in the error term. And then this is our expression, or our approximate expression for d square phi dx square. We set that equal to S phi to satisfy our governing equation. Okay, and we end up with that equation right there. We rearrange it so that we put all the knowns on one side, all the unknowns on the other side. Okay, the knowns are, these guys are all known. The source term is known, C, A, B, those constants are known. Okay, so we have all the knowns on that side, and then on the left hand side we simply have everything that contains those unknowns. All right, set it up in matrix form. This is what we get. So again, if you go back here, so phi n gets multiplied by negative 2 over delta x squared times 1 plus b over a delta x, which is what we have here, and then the other guy has a 2 over delta x squared in front of it. Okay, and whatever we had in the right hand side ends up going there. All right, this is first order accurate, so we still have a tridiagonal system. If you use the same idea to do second order accurate, you will find that something will show up here instead of a 0. Okay, but the procedure is exactly the same. Any questions? All right, so that brings us to the end of how to do boundary conditions.